Ladies and gentlemen, class recording has begun. So, on Friday, we were talking about orbits, and we were talking about how gravity, if acting on an object in a specific way, can cause that particle to change directions, but won't necessarily change its speed. So gravity acts as a centripetal force, and it causes that object to go in a curved path. And if the speed is just right, we can make ourselves a nice little circular path for an object to travel around another object, all due to gravity. If that speed of that object isn't exactly right, we can get it to, that object will not move in a nice circular path, but will instead move in an elliptical path. And we talked about that as it travels along that path, sometimes it will speed up, sometimes it will slow down, based on whether it's going towards the object it's orbiting or going away from the object that it's orbiting. And that those, you guys didn't get to the stuff at the end about Kepler, huh?
No, they came in and we're trying to bridge out the window.
All right, so let's go there. That's kind of important. All right. So, if you have, he's waiting in the wings, so we're going to get to him a little bit. All right, if you have the notes from Friday, the ones that say satellite motion on them, go ahead and pull those out because we didn't quite finish those up.
This one?
Yep. Nope, that's one from Thursday. The one from Friday is a satellite motion. Aaron's up at the front. So what's a satellite motion on this? Yes. All right. So, to quickly review, when Newton realizes what gravity is doing and what gravity is, he starts messing around a little bit more with the numbers, and he realizes that he knows gravity will pull an object down a certain amount in 1 second. That amount is about 5 meters, a little bit less than 5 meters, but whatever. Yep. But he then says, well, I can figure out then, knowing the curvature of the Earth, how fast something would have to travel horizontally. Yeah, no, we're just reviewing. How fast something would have to travel horizontally in order for it, that in the time that it falls 5 meters downwards, the Earth has curved 5 meters downwards, and then we've gotten no closer to the surface of the Earth, not because gravity hasn't acted on the object, but because as it was acting on the object, the ground curved and we end up the same distance. And that is a circular orbit. And we talked about the idea that figuring out how fast something would have to go is a problem that we did last chapter. F of c equals f of g, where f of g is not m times g, but that formula that Newton came up for the force of gravity between two objects. Okay? You'll notice here m1 and m1 cancel in this formula because they're on both sides. That's the object that is orbiting. So we find out that the speed something would have to go in order to orbit the Earth or whatever else only depends on the mass of the Earth, not the mass of the thing orbiting. So a spaceship has to go the same speed as an astronaut in order to create a circular orbit because gravity acts on all things the same way.
Do perfectly circular orbits ever happen?
Sometimes yes, okay? But that was kind of like the progression of this, is that this is a real specific speed. That, a circular orbit depends on the mass of the object and how far away you are. And that's one number. You get an answer for V. If you're not on that speed, you don't make a perfect circle. Does it happen? Yes, sometimes it happens. It just depends on what we want to do, okay? But most of the time, we're not at that perfect speed. So we talked about the idea that once it gets off of that speed, satellites that are speeds greater or less than the calculated specific circular orbit move off of that path. If it's less than this speed, if it's less than the circular orbit speed, what's eventually going to happen? It's going to fall out of orbit and crash into the ground eventually, okay? But if it's greater than that speed, now we get this oval path that we called an ellipse, right? And we talked about the idea that in certain parts of this orbit, the object does not travel at a constant speed. that as this object is moving outward, there is a, did we get to the components of gravity here? Not at all? Man. So, all right. Oh, that's right. How could I forget? Teachers interrupting education. I forgot about that. So, all right. Let's start with this picture.
Wow.
We can turn those speakers off over there. All right. If we take a look at this blue line, that blue line representing a circular orbit, right? The force of gravity that exists on that object points this way, right? The object is trying to go this way. Does this picture look familiar? I hope so. We drew it like 500 times last chapter, right? The satellite is trying to go straight, that's the blue dotted line. Gravity's pulling on it downward, that's the green solid line, right? And then we get somewhere in the middle. If the speed is just right, those things will just keep happening. But once again, this is probably not going to be worth what I'm trying to do, but that's okay. Alright, so that applies right here, okay? But if that object moves over to here, right? We take this thing, now it looks like this, right? And if that just keeps happening over and over and over again, now we get a circle. Okay? Good. All right. Just don't put Einstein in any compromising positions, that's all.
What if the speed is greater than the perfect amount?
Okay. If the speed is greater than the perfect amount, and that's where we're going with this, okay? Here, if the speed is greater than the perfect amount, you still got the satellite that's trying to do this, okay? But now it's longer, greater speed, right? And you still got this gravitational force that's pulling here, okay? That speed that calculates from the circular orbit formula makes it nice and even so that gravity is always exactly perpendicular to this path. Okay? But if this speed is too great, it won't go in a nice circle. It's going to bow outward, right? Because it's not enough force to make it go in a complete circle. But it is still enough force to cause it to change direction. Okay? So what ends up happening is, on the way out, this object is still trying to do this, okay? But gravity now is pulling it like this, because gravity always points towards the middle of whatever's pulling it back together, right? Okay, we learned that the other day. So now, we end up with this. Okay? Does that make sense what I just did?
Yeah.
So I break gravity up into components. This component right here, it's acting how in relation to the path of the object? Perpendicular. So it's going to cause it to do what? No. Things that act perpendicular cause it to do what? Go in a circle, or at least, Bridget, more generally change direction. Okay? But this one, which way is this one acting in relation to the way that it's going? Opposite. So what is this component going to cause that object to do? Slow down. So on the way out, it still curves, but it slows down until it reaches this point way down here. Okay? Does that make sense, Kevin?
Yeah.
Okay? At this point, when it's at its very, very farthest, here's gravity. Okay? And now it's acting perpendicular. But what's been happening the whole time to this object as it's been going out? Slowing down, slowing down, slowing down, slowing down. Guess what? Now the speed isn't right to make a circle out here. It's too slow. So we said that starts kind of pulling it back in towards the object. But on the way back in, there's the speed of the object. There's gravity. Okay? What's this one causing the object to do? That one's not causing it to speed up, it's causing it to do what? Because that one's perpendicular. But now what's the other component causing it to do? Speed up. So, these things will slow down on the way out, speed up on the way back. Slow down on the way out, speed up on the way back. Okay? In an elliptical orbit, orbital speed changes. As the satellite moves away from the object, it slows down. Why? Because there's one component of gravity that's pulling it back. But when it's coming towards an object, it speeds up. Why? Because that component of gravity is now pulling it towards that object, causing it to go faster, faster, faster. Have you ever heard of the concept of using gravity to slingshot around something? Okay? Guess what you do? Apollo 13. Yeah, you ever see Apollo 13? It was a really bad movie back in the 90s called Lost in Space. Anybody ever see Lost in Space? Terrible. Okay. But anyway. But yeah, in Apollo 13, they used the moon's gravity to slingshot around the moon. Because they didn't have enough gas. So here's Apollo 13. Okay? We'll make Apollo 13 and we'll draw it. So here's it's not going to be good, just so you know. And like that. And then there's kind of like, I don't know, something like that. So,
It's just like it.
totally. It's exactly what it looked like. Anyway. So you get Apollo 13 in a elliptical orbit around the moon. The whole time it's getting closer and closer and closer to the moon, what's happening to it? Speeding up, 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 speeding up until it gets to here. At that point, what do? Well, it would start slowing down if you didn't do anything. But now, it's gone faster, 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 faster. So what do you do now? Hit the gas. Because now, you've gone faster, 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 and not had to use any gas. Gravity has just been making it go faster, 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 faster. At that point right there, you hit the gas. You're already going fast, now you go faster. Okay? This happens to things in elliptical orbits. Slow down on the way out, speed up on the way back. Slow down, speed up. Slow down, speed up. Okay? Depending on how much of an ellipse this object is, or orbit is, the speeding up and slowing down is more dramatic. Okay?
What about like the space station and stuff? Are they like elliptical like that?
A lot of times they'll put things purposely in elliptical orbits because also too, Tyler, not only do they speed up and slow down, but where are they? Here, they're real close to the thing they're orbiting. Here, they're real far away. Sometimes you want to be closer to the thing you're orbiting, sometimes you don't, right? If you're orbiting the moon, right, you want gravity to sort of bring you in. Now, granted, it's making you go faster, 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 but it is bringing you closer, right? Sometimes you don't want to be that close. Sometimes you want to be farther away so you can get a better picture or whatever it is that you're doing. Okay? So yeah, a lot of times it will be that we'll purposely put things in elliptical orbits in order to do whatever purpose that thing is serving. Now, sometimes, like with a GPS satellite, do you guys know how GPS works? GPS, regardless of what kind of GPS, whether it's your the GPS like in your car, or whether it's like Google Earth, or whether it's like your phone giving you directions, okay? There are 24 satellites that orbit the Earth, and they are really far out because they are in completely. This is a circular orbit thing, okay? But it's in a perfect circular orbit that it's orbiting at exactly the same speed that the Earth turns, so they don't move from their spot. Does that make sense? That if they're orbiting at the same speed that the Earth rotates, they stay directly above where they are on the Earth. Call it a geosynchronous orbit. So that satellite and always in the same spot. That one you want to be in a circular orbit because you don't want it to change speed. You want it to stay with the Earth. So now there's always a reference point. Okay? Say again? So yeah, do we want to do things sometimes? Yeah, we do. Okay? All right. Good with this idea for now? Okay. Why is this important? Well, now we use it to like do satellites and use Earth or gravity to slingshot around things and stuff like that. Okay. But back in the day, it explained a lot of stuff. So here's two guys. Oh. Let down. I built it up and then just. Yeah. So here's two guys. This is Kepler. This is Bra. His name's actually Brahe, but Bra's better. check out Bra's collar right here. It's pretty sweet. So Kepler's got himself a little like flower action going on here, but anyway. Yeah, his mustache is pretty good. Somebody pointed out too that like the nose just on Bra wasn't just maybe this artist was like just good at everything, just never could get noses right. I don't know, but whatever.
Well, I was on a budget. You got your guy who can't do the nose.
Yeah, he's like I'm pretty good with eyes and ears, but don't ask me to do a nose. He's like, yeah, that's all right. All right. So back in the 1400s, notice 1400s. Okay, this is like 200 years before Newton comes around. No idea about gravity or how it works. They knew what gravity was, didn't know why it worked, and stuff like that. So Brahe basically sits around at night and makes a whole bunch of measurements. Positions, stars, planets, moon, sun, all these things that show up in the sky. Just makes measurements, real precise measurements, over and over and over and over and over again. Night after night after night after night after night. Okay? So then Kepler gets Brahe's data because he's his student, and he starts looking at all this data. And he finds out, he starts seeing patterns in this data. Weird things that come to certain conclusions, okay? So Kepler looks at this data, starts finding patterns, looks at relationships, and comes up with 3 laws for planetary motion. So the first thing that he comes up with is that, okay, all these things that are out there, planets mostly, but comets too, and stuff like that, they're not in nice circular paths. They're in elliptical paths. And the sun is at one focus. This picture right here shows an ellipse. Mathematically, an ellipse, there are 2 points. And if you take, like, the easiest way to do it is kind of make a string, and you make a triangle, and the 2 sides of the triangle always add up to the same number, but one side gets bigger and the other side gets smaller, and blah, blah, blah. Does that sort of make sense as far as what an ellipse is? Okay. A circle is a perfect ellipse, where these 2 push pins are both exactly in the middle. Okay? So a circle is an ellipse, but not all ellipses are circles. But what Kepler says is that planets are taking elliptical paths where the sun is at one focus. So Kepler, early 1500s. Why is this a problem?
Because the Earth is the center.
Yeah, God said the Earth was the center of the Earth. Now, Kepler's saying, wait a second. No, it's not. Okay? Also, what paths are these things taking? Elliptical paths. Why is that a problem? God doesn't do ellipses. God does circles. Why? God's perfect. All right? He doesn't do ellipses. He does circles. Okay? But Kepler's looking at data going, no, it's not really what it is. Okay? Monty, go ahead.
So if the planets do the elliptical
Yep.
path, how come all the seasons are kind of the same length?
That has, Monty, our seasons are more responsible because of the way Earth is tilted as opposed to how close or far away we are from the sun. Okay? It would make sense, for us, if we go back to this picture, it would make sense that this is summer and this is winter, right? But in actuality, for us in the northern hemisphere, this is summer and this is winter. Now, obviously, this is a little exaggerated, okay? But we are actually closer to the sun in our winter time than we are in our summertime. But because our axis is tilted, during the summertime, we're farther away from the sun, but we face it more directly. So we get like more direct sunlight. Does that make sense? Okay. Can you see that model up there in the top corner? That's basically summer for us because of the way it's tilted. Okay. If you swing it around the other way, we still say tilted this way, but if you swing it around the other side, now we're not getting like direct sunlight, and that's winter for us.
So if we weren't tilted and we were just like straight,
Yep.
like all our seasons would be all.
Yeah, our seasons would be opposite basically of what they are now. They would be a little bit more what the southern hemisphere is like, but once again, the southern hemisphere isn't getting summer because it's closer to the Earth. It is closer to the Earth during its summertime, but it's more responsible because the southern hemisphere would then be tilted towards the sun at that point. So in theory, should summer times in the southern hemisphere be more hot than our summer times? In theory, yeah, because we're closer to the Earth and it's tilted. Is it? Kind of depends on where you are more than anything. So north, south. Does that make sense?
Yeah.
But yeah, but if we didn't tilt, then yeah, our summertime would probably be flipped from where it is now because we're closer to the sun then. We get more sunlight. But on the other side, we would get less because we're farther away. Okay. All right. Second law. Second law. This one's kind of weird. Okay. Second law says, so here is June 1st, and here's July 1st. So point A is where we are in June 1st, and point B is where we are in July 1st. Okay. Point D, if we're going around in this fashion here, point D, that's November 1st, and this is December 1st. Okay? Notice, both of them make a triangle, yes? Okay? But this one is a tall, skinny triangle, and this one's a short, fat triangle. Same area of the shaded, if you take the area of this, now I know it's not a triangle, right? It's not a curved side, okay? But the triangle, in quotations, right? The area of this triangle is the same as the area of this triangle. The only way that happens is if we're going slow out here, and we're going fast in here. Okay? This is stuff that Kepler is noticing from data. He's got no idea why, he just notices that it happens. How does he notice it happens? Well, that's we just talked about why that happens, right? Because of the way gravity works. Back in the day, he didn't know why it was happening, he just knew it was. Okay? The other thing that he notices, okay, this is a big crazy equation, all right, that did not copy well, it did not print out on the back side. Okay, sorry. So T of A squared over T of B squared equals R of A cubed over R of B cubed. So there's a bunch of words over here on the side, okay? But the words get summarized like this. Basically what that's saying is that the closer you are to the sun, the faster you go around your orbit. The farther you away from the sun, slower you go around your orbit. Okay. Say again. Closer you are to the sun, the faster you go around your orbit, the less time it takes you to go around. The farther you are, the more time it takes you to go around. If we go back to this equation, now granted we said this isn't exactly right, okay, because it's not a complete circle, but as distance gets greater in the bottom of this fraction, what happens to speed? If the bottom of this fraction gets bigger, what happens to the speed? It gets slower, right? Inverse relationship. Okay. So that means the farther you are out, the slower you go around your orbit. And that's what Kepler is seeing. Once again, he has no idea about why it's happening, but once Newton starts introducing this idea of gravity, now it all makes sense as to why these things are happening. Okay?
I just have a question about how a lot of people are saying that there's global warming. Does that have anything to do of our orbits and stuff?
No, it has to do with the atmosphere surrounding us.
No.
So that
So
we're
not
basically,
closer to the sun.
no,
longer.
we're holding on to more of the energy from the sun instead of it bouncing off of us. So, Kepler throws out these three ideas. Now, as we've discussed, right? As we've discussed, are these kosher with God, which I realize is kind of a mixing religion sort of thing, but do these things jive with what God is saying? No, right? So what does Kepler do? He writes a book, right? Explains all these things, and then he publishes about a month before he dies, because he knows that if he throws these things out here, yeah, the Pope's going to be not happy about this, right? So, but anyway, Pope is going to totally kill you, dude. Right? But anyway, so, but those things all get explained later on with Einstein, or sorry, not with Einstein, with Newton and his gravity thing. Okay? All right. So now, the question that leads us into the next part for today. We've talked about what happens if you're going at a perfect speed to make a circle. You get a circle. Okay? If you're going too slow, if you're going too slow, what happens? If you're going slower than this speed, you eventually crash into the earth. If you're going faster than this speed, you make the ellipse.
Could you go fast enough where you just
That was a great question.
Good question, Ben.
Ben,
All
can
right,
you say
so-
it again?
Okay. Escape speed. What goes up has to come down, right? Well, maybe not. Okay. So it starts, our discussion of escape speed starts with this relationship. The inverse square relationship, meaning the farther we get away from something, how much gravity is there? There's less gravity. So technically, as I throw this ball up into the air, what happens to the gravity acting on it? It actually decreases because I'm farther away from the center of the earth. Now, is it enough for us to perceive? No, but it does decrease. The farther and farther and farther we get, the less and less and less gravity there is. We talked about that in theory here, the only way that you could get F in this equation equal to 0 would be you can make either M1 or M2 0, but then you don't have enough objects to do gravity. Or, what could we do with D? You could increase it to what? The only way we can get a fraction equal to 0 over here, if the bottom is 0, it's undefined. The bottom of this fraction has to be infinity. If you put infinity, the biggest number possible on the bottom of this fraction, you would get the smallest number possible here. Does that make sense? Hey, we're recording and you're sitting right next to the microphone. So, the force of gravity between two objects would only go to 0 if the distance between them was infinity. Can you do that? Can you get infinity meters? Can. So in theory, you can't, there will always be a force of gravity. So could you ever launch or throw something fast enough that it would escape the gravity of an object? In theory, no. But we find out that that's not the case out there in the real world. That's true. So maybe that equation isn't right.
So everything's object is always acting on everything?
Yep.
These, no matter how small it is?
No matter how small or how far away it is. Okay? Now, this is how escape speed works. So we kind of get this idea that as this object goes up, what happens to its energy? It gains what? Potential, but it loses kinetic. And on the way back down, it gains kinetic and loses potential. So let's say we could calculate how much energy, potential energy, this object would have at infinity meters, which is not possible, but there comes a point when the energy is so small that it's pretty much zero. So if I say, okay, if I want this object to go this high, right, this lady in the building, and she has 10,000 joules of potential energy, how much energy would I have to give it at the bottom to make it go that high? 10,000 joules. Okay, we did that problem when we did energy conservation and stuff like that. But let's say I give this ball 10,001 joules of potential or kinetic energy down at the bottom. Does it stop at the top? No, it goes a little higher. If, in theory, we could give this object more potential, or sorry, more kinetic energy down here than it would have at the highest level of potential energy, when it gets there, what would it still be doing? It would still be going. And if we're basically out of gravity, what will it keep doing? It will keep going.
So if you were in an airplane and you, what? No. If you were like, I don't know, just really, yeah, a rocket, and you shot a gun up in the air, like would the bullet just keep going and go? Oh.
Not fast enough. Okay? But there is a speed that we could shoot at Imani that it wouldn't come back. Okay? This, I mean, what's the difference really between a gun and a rocket?
I know what I'm saying, like,
You could.
like if they were on the moon. Like,
You could, because it depends on a little explosion inside the gun, and that would work in
what
space.
would it do after you shot it?
You'd fly back, yeah. So, and there'd be nothing to stop you because of the whole Newton's third law thing, you know? You probably don't want to shoot that. You probably don't want to shoot that gun in space. All right. So,
I got a question.
Go ahead.
So say you're going to a rocket straight up.
Yeah.
You shoot a gun straight down. What happens?
well, the
Will
gun.
the bullet even come out though?
Yeah. It would, I mean, yeah. 'Cause, you know, I mean, if I'm walking backwards, I can throw the ball this way, you know. But it would also make you go a little bit faster too, right? Because of the whole Newton's third law thing. You know, if you push the bullet down, it's going to push you up.
Yeah.
So that would actually help your case as far as escaping gravity.
But you're going so much faster than the bullet.
That's true, but it still happens. Because the bullet, when it's in the gun, is still going basically just as fast as you. Actually, we'll get into that tomorrow, that the bullet really doesn't know how fast it's going. All it knows is that you and it are going the same speed. Okay? That gets into some Einstein stuff tomorrow. So.
You just really messed them up.
Where'd you go? Could. Okay? But depending on the direction, you might get yourself into either an elliptical orbit, or if the speed is right, no orbit at all. All right. Whoa. Hey. It's got like 4 minutes left. 4:11:08. I have a clock, so I know what time it is. So we start looking around in the universe, and we find a couple of things. We find this crazy thing called a black hole. Now, a black hole, first of all, we can't really see a black hole, because a black hole gobbles up everything, okay, including light. So all we see is a big black space and a bunch of stuff heading towards that big black space. So our deductive powers of reasoning go, oh, there must be a lot of gravity there. Okay? But where does it come from? So black holes usually form at the end of a star's life. After a big explosion of a star, a really big star, not like our sun. Huge. Okay?
Wait, so is that our sun?
Nope, not enough mass.
Oh, no.
So, what happens is, okay, actually here, let's do this. So if we go here, Tyler, okay, this is the escape speed. This is how fast you would have to go to get away from the gravity of that object, okay? This is the mass of the object you're trying to get away from. This is how far away you are from it, okay? What happens in a black hole is that this V value right here ends up being greater than the speed of light. So the speed of light is the fastest thing we know in the galaxy. So even if I was standing on the black hole and I threw something at the speed of light upward, which obviously there's some logistical problems there, right? But even if I threw it up, that ball would go up, stop, and come back down. Okay? But here on Earth, if I throw something the speed of light, it just goes. All of the radio signals that we send out and everything like that, they are just out there. And they just keep going and going and going. And you know, maybe somebody picks them up somewhere in the universe and sends them back to us or whatever, but those speeds are great enough that they don't come back. Okay? So we'll talk a little bit more about this tomorrow and talk about how that happens, even for light. Because if you're paying attention to our discussion of gravity, light being sucked into a black hole should present a problem to you. Okay?
I mean, light